Hello, Divas. This is my student ID, and following is the video presentation for part 2 of assignment 1. Here is the word class. What this represents is it encapsulates the literal word within our dataset into this class while storing some important field data like the frequency and list of neighbors. The increase frequency functions basically increases the frequency of the word if it is invoked upon that word. The two string representation functions return the string representation, and um, I have some comparison methods that help us compare the word objects during the sorting process. The isNeighbor function basically provided two words. It checks whether those two words are neighbors or not using the criterion that was provided in the assignment. Um, so on this section, I have chosen to represent my data structure in my lexion in a dictionary because the biggest bottleneck in my previous assignment was finding all the neighbors of a word. So for each of the words, we would have to iterate over the data set again and again, and that was the biggest bottleneck. So the reason why I chose this data structure is it significantly reduces that bottleneck because in this data structure, what I do is the key represents the length of a word and the values represent all the words in our dataset that have that length. So if I want to look for the neighbors of the potential neighbors of a word with length 3, I would just have to look at the data at the dictionary at the dictionary of diction at the key value of at the key value of 3, and it will basically provide me with all the words that have that particular length. These are the read write functions. The read data function, it opens the file, iterates over the file line by line, and then provides and applies filter, removes all the non-alphanumeric characters, checks whether it's empty or not, and then what this does is it tries to find whether a word of similar length has already been added to our lexion. If it's not added, it initializes an empty array. If there has already been a word of similar length, then it gets fetches all the values of that key and iterates over the values. If it finds that it has already the same word has already been added, it increases the frequency. Otherwise, it just appends to that array. Similarly, write data just opens up the file, um, merges the sorry m- sorts the data using the flatten list. The flatten list is basically um, all the value string, all the array of values, all the array of values corresponding to all the keys in the dictionary combined into a single array. So it uses the same merge sort algorithm that I used in my previous assignment, and then writes to a file after it has been sorted. The flattened lexion, what this does is it takes the lexion and basically combines all the value arrays into one single array for sorting. This is the same sorting function that I used in my previous assignment. The add neighbor function, what this does is this time instead of iterating over the entire data set, it just subsets the dataset using this. So what it does is it fetches all the words that have the particular length of the word that we are operating on, and it just iterates over there, checks whether the word is a neighbor or not, and appends to it. After finding out all the neighbors, we merge sort all the values. The biggest bottleneck was removed using this filter, which basically significantly reduces the number of comparisons that we will have to make. The build lexion is just for um, the build lexion reads all the data from our data set, flattens the list so that we can sort while writing, and add na- adds all finds all the neighbors and writes the data. So I'll run this. I'll run this code above. Yes, it runs, and I'll run this code as well. As well. It should take some time. So in the meanwhile, I will explain part two of my assignment. Sorry, section two. In here, I have implemented the skip list. Now, skip list is just like a linked list, but unlike a linked list, each node also stores additional pointers that point to the different lanes within that with different lanes within that skip list. Now, lanes are basically path reduced. Lanes are basically reduced um, lists that have fewer elements because they skip over multiple nodes at a time. So it can have multiple lanes. It can have lanes that are more faster than the one more faster and more slower, and there is one normal lane which is basically the normal linked list. So here I have initialized the word, the pointers for the different levels for each word, and this is the skip list. I have initialized it here. I have set the maximum level as provided here, so it can have a maximum of 16 different levels. And here is the probability variable. So this is used to determine in a particular lane whether a word will come or not. And I have set the value to 0 0.5 because it gives a equal chance of a word falling in the lane or not. The head is first the head is the first word that's the head is the first word that's in the particular lane, and the level is set to 0. So what the random level function does, it generates a random level for a specific word. So it can be determined in which level the word is going to be added to. Uh, the search uh, the search function, what this does is it finds whether a word exists in the skip list or not. Now, how we find a particular word is we start from the highest lane, the express lane, and we compare whether the word is less than or greater than in each of the in each of the express lane nodes. And if we find that it's less than a particular node, then we move on to the lower level, which which has more nodes, and perform the similar checks until we either find the word or we reach down to the normal lane. And still, if we still don't find them, then it means that the word is not present. So this loop is used for gradually iterating downwards from the highest lane. Um, at each uh, at each uh, at each iteration, it checks uh, whether the word is smaller than the target that we're checking, and it reduces the lane at each iteration. If the if the if the word we are iterating at if the word we are looking for matches the word that we have right now, then we can say that the word has been found and we just return the word. Otherwise, we return none, and that means the word does not exist in the skip list. Similarly, in the insertion process, what we do is we first try to check whether the element is already in the skip list or not. It's similar to the sorts logic. We start from the highest lane and gradually move down towards the normal lane until we find it. Um, if we find it, we just increase the frequency and return back that word. If we do not find it, then we'll have to insert it. Now, what we have to first do is we have to choose a random level for it. We use the random level that we implement that I explained earlier. What this does is it gives a random level to this word which has to be less than the max level that I have initialized here. Yes, after that, it generates a word using the string target. It generates a node that will be fitted into the skip list and updates the pointers of the nodes such that the word can be fitted in the appropriate position. Now delete. It also has similar logic. It first searches whether there is a word in the skip list or not. If there isn't a word in the skip list, what this does, uh, if there isn't a element in the skip list, it just returns false. If there is an element in the skip list and it matches to our target, then it it just delinks. It just removes the pointers of its previous node and delinks the node from the skip list. Now, to sorted list just removes the flattened version of the skip list. And these are the read write operations that integrate the skip list. Uh, the read data skip list opens the file, applies filter to them, and reads each word and adds each word to the skip list. Similarly, add neighbors. This just iterates over the flattened list and adds neighbors add neighbors and sorts them. The write data skip list basically opens the file and iterates over the sorted list and writes the data to the file. Build Lexion is just for reading the files, flattening the data, adding neighbors, and writing data. So I will run both of these codes. Both of these code run without any error, and I will run this, and yeah, it runs without any errors. And I think the previous code section also ran without any error. Yeah, it also ran without any errors. It took 40.30 seconds across two different runs.